James Webb Space Telescope has just discovered galaxies that should not exist. Objects so old and so massive they seem like they are not from our universe. And what scientists are finding is shaking the very foundations of everything we thought we knew about how the cosmos began. If you are fascinated by the mysteries of the deep cosmos, please like this video and subscribe to Cosmic Drift for more journeys through the stars. Now, here is the thing. We have spent decades building our understanding of the universe. We have studied the stars. We have mapped the galaxies. We have traced the light back to the very beginning of time itself, and we thought we had it figured out. We thought we knew how galaxies were born, how they grew, and how long that process was supposed to take. But then the James Webb Space Telescope opened its golden eyes and looked deeper into space than any instrument ever built. And what it found made scientists around the world say the same thing. That is impossible. These are not just any galaxies. These are monsters, behemoths nearly as massive as our own Milky Way, packed with hundreds of billions of stars. And here is the part that keeps astronomers awake at night. These galaxies existed when the universe was just a baby. We are talking about 500 to 700 million years after the Big Bang. The universe is 13.8 billion years old today. That means these galaxies formed when the cosmos was only about 3% of its current age. To put that in perspective, imagine a 100-year-old person. At 3% of their life, they would be just 3 years old. A toddler. Now imagine finding a 3-year-old child who somehow already looks like a fully grown adult. That is what scientists found in these images. Baby galaxies that look like they have already lived full lives. The team that made this discovery could not believe what they were seeing. Erica Nelson, an astrophysicist at the University of Colorado Boulder, put it in the simplest terms possible. She said it is bananas. You just do not expect the early universe to be able to organize itself that quickly. These galaxies should not have had time to form. But there they were, 6 fuzzy red dots glowing in the darkness of the ancient cosmos. And those little dots are about to change everything we think we know about the universe. So how did we get here? How did we go from thinking we understood the universe to suddenly questioning everything? To answer that, we need to understand what the James Webb Space Telescope actually is and why it can see things no other telescope ever could. The James Webb Space Telescope, or JWST for short, is the most powerful observatory ever launched into space. It is not just a better version of the Hubble Space Telescope. It is something entirely different. Think of Hubble as a pair of regular eyes looking at the universe. JWST is like having eyes that can see in the dark, through walls, and back in time. The secret is infrared light. You cannot see infrared with your eyes. It is the kind of light that comes from heat. When you hold your hand near a warm stove, that warmth you feel is infrared radiation reaching your skin. Everything that has heat gives off infrared light, even if it is invisible to us. Now here is where it gets interesting. The universe is expanding. It has been expanding ever since the Big Bang, 13.8 billion years ago. And as space expands, something strange happens to light traveling through it. The light gets stretched. Imagine drawing a wave on a rubber band and then pulling the rubber band from both ends. The wave gets longer and more spread out. That is exactly what happens to light as it travels through the expanding universe. Scientists call this redshift because the light shifts toward the red end of the color spectrum. And if light travels far enough through expanding space, it shifts all the way past red into infrared. This is why the oldest galaxies in the universe are invisible to telescopes like Hubble. Their light has been stretched so far that it has become infrared. Hubble can see some infrared, but not much. It was mainly designed to see the same kind of light your eyes can see. JWST was built specifically to see infrared light, and not just a little bit. It can see wavelengths of light that have been traveling for over 13 billion years. Light that left its source when the universe was just a few 100 million years old. Light from the very first stars and galaxies that ever existed. But seeing infrared light is tricky. Here is the problem. Everything warm gives off infrared radiation. Your body does. The Earth does. Even the telescope itself does. If JWST were warm, it would be blinded by its own heat. It would be like trying to see the stars while someone shines a flashlight directly in your eyes. So the engineers who built JWST came up with an incredible solution. They put a massive sun shield on the telescope. This shield is about the size of a tennis court, and it blocks light and heat from the sun, the Earth, and the moon. On the dark side of that shield, the telescope is chilled to an unbelievably cold temperature. We are talking about negative 370 degrees Fahrenheit. That is just 50 degrees above absolute zero, the coldest anything can possibly get. At that temperature, JWST does not give off enough infrared light to interfere with its observations. It can sit there in the freezing darkness of space and stare at the faintest, most distant objects in the universe without being blinded by its own warmth. And then there is the mirror. The primary mirror of JWST is 21 feet across. That is more than 6 times the surface area of Hubble's mirror. A bigger mirror means more light-gathering power, and more light-gathering power means JWST can see objects that are 100 times fainter than what Hubble could detect. So when JWST turned its infrared eyes toward the ancient universe for the first time, it could see things that had never been seen before. And almost immediately, it started finding things that made no sense. Let us talk about what scientists expected to find versus what they actually found. For decades, astronomers have had a model for how the universe works. It is called the Lambda CDM model, and it is the best explanation we have for everything from the Big Bang to the galaxies we see today. Lambda stands for dark energy, the mysterious force that is making the universe expand faster and faster. CDM stands for cold dark matter, the invisible stuff that makes up most of the mass in the universe. According to this model, the universe began 13.8 billion years ago in an unimaginably hot and dense state. In the first fraction of a second, it expanded faster than the speed of light in an event called cosmic inflation. Then it cooled down. The first simple atoms formed, mostly hydrogen and helium, the lightest elements in existence. But here is the important part for our story. According to the model, galaxies did not just pop into existence. They had to be built piece by piece, and that process was supposed to take a very long time. First, dark matter had to clump together into structures called halos. Dark matter does not interact with light, so we cannot see it directly, but it has gravity, lots of gravity. And that gravity slowly pulled ordinary matter, the stuff that makes stars and planets, into these dark matter halos. Once enough ordinary matter collected in these halos, it started to condense and heat up. Eventually, the first stars ignited. These early stars were probably different from the stars we see today. They were made almost entirely of hydrogen and helium because heavier elements did not exist yet. They were also probably much bigger and brighter than modern stars. When these early massive stars died, they exploded as supernovas. Those explosions created heavier elements like carbon, oxygen, and iron. And those elements were scattered into space, where they mixed with gas and eventually formed new generations of stars. Slowly, over hundreds of millions of years, these small clumps of stars merge together. Little galaxies combine to form bigger galaxies. And those bigger galaxies combine to form even bigger ones. It was a slow, gradual process, like building a house one brick at a time. According to this model, the very early universe should have been filled with tiny, young galaxies, little clusters of stars just starting to form, not full-grown behemoths like the Milky Way. That would come later, after billions of years of growth and merging. This is what scientists expected to see when JWST looked back in time to the first billion years of the universe. They expected to find baby galaxies, small, faint, still in the early stages of formation. But that is not what they found. When the first data from JWST started coming in, a team of astronomers from around the world began analyzing the images. The team included researchers from the United States, Australia, Denmark, and Spain. They were looking at data from something called the SEER survey, which stands for Cosmic Evolution Early Release Science. The survey focused on a small patch of sky near the Big Dipper, a region that had been studied before by Hubble, but never with this level of detail. As they pored over the images, something strange started to emerge. There were these fuzzy red dots scattered throughout the pictures. Dots that were incredibly bright for objects so far away. Dots that Hubble had never seen. Erica Nelson was one of the first to notice them. She was flipping back and forth between Hubble images and JWST images of the same region of space. And suddenly, these extremely red, extremely bright objects popped out at her. Objects that simply did not exist in the Hubble pictures. At first, the team thought they must have made a mistake. Maybe there was something wrong with the data. Maybe they had misread the measurements. Joel Leger, an astrophysicist at Penn State University, described the moment perfectly. He said, "My first thought was, we had made a mistake, and we would just find it and move on with our lives. But we have yet to find that mistake, despite a lot of trying." The more they analyzed the data, the more impossible the results seemed. These 6 fuzzy red dots appeared to be galaxies. Not just any galaxies, massive galaxies. Galaxies with almost as many stars as the Milky Way has today. And they existed when the universe was only 500 to 700 million years old. Let that sink in for a moment. The Milky Way has had 13.8 billion years to grow to its current size. It contains somewhere between 100 and 400 billion stars. And it took all that time, billions upon billions of years, for our galaxy to reach this point. But these newly discovered objects appeared to have achieved the same thing in just 500 million years. That is about 3% of the time. It is like a baby going from birth to fully grown in a single year. Joel Leger summed up the situation in stark terms. He said these objects are way more massive than anyone expected. We expected only to find tiny, young, baby galaxies at this point in time. But we have discovered galaxies as mature as our own in what was previously understood to be the dawn of the universe. The team published their findings in the journal Nature in February 2023, and the paper sent shockwaves through the scientific community, because if these galaxies were real, then almost everything we thought we understood about the early universe was wrong. The scientists gave these mysterious objects an unofficial name. They called them universe breakers, and they chose that name for a very good reason. According to Leger, these galaxies are in conflict with 99% of models for cosmology. Let me repeat that. 99% of our mathematical models for how the universe works cannot explain how these objects could exist. Think about what that means. Scientists have spent decades building and refining these models. They are based on observations from countless telescopes, satellite missions, and ground-based observatories. They incorporate everything we know about physics, from general relativity to quantum mechanics, and they work. They successfully explain the cosmic microwave background radiation, the distribution of galaxies throughout the universe, the abundance of different elements, and the accelerating expansion of space. But these 6 fuzzy red dots broke the models. Not just bent them, broke them. As Leja put it, we looked into the very early universe for the first time and had no idea what we were going to find. It turns out we found something so unexpected, it actually creates problems for science. It calls the whole picture of early galaxy formation into question. Now, before we go any further, I need to explain something important. When scientists say they found galaxies from 500 million years after the Big Bang, how do they actually know that? How can you measure the age of something that is so unimaginably far away? The answer has to do with something we touched on earlier: redshift. Remember how light gets stretched as it travels through expanding space? The further light has to travel, the more it gets stretched. And the more it gets stretched, the redder it becomes. So by measuring exactly how much the light from a distant object has been redshifted, scientists can calculate how far away that object is. And since light travels at a fixed speed, knowing the distance also tells you how long the light has been traveling, which tells you when the light was first emitted. It is like a cosmic clock built into the light itself. For the universe breaker galaxies, the measurements showed extreme redshift. The light had been traveling for over 13 billion years. It left those galaxies when the universe was just a small fraction of its current age. But here is the thing. Redshift measurements can be tricky, especially for objects this far away. The initial findings from JWST were based on photometry, which is essentially measuring how bright an object appears in different colors of light. It is a bit like looking at someone from far away and trying to guess their age based on how they look. To be absolutely certain, scientists need spectroscopy. This is where you spread out the light from an object into a rainbow of colors and look for specific patterns. Different elements leave distinctive fingerprints in the light they emit. By finding these fingerprints, scientists can confirm exactly how far away an object is, and even figure out what it is made of. At the time of the initial discovery, the team had not done full spectroscopy on all 6 universe breakers. They had strong evidence based on photometry, but they knew they needed more data to be absolutely sure. And this is where the story gets even more interesting. As other scientists analyzed the same data and conducted follow-up observations, they started finding more of these impossible objects. Not just 6, dozens, then hundreds. The early universe, it turned out, was not the barren wasteland of tiny baby galaxies that everyone expected. It was full of these mysterious red dots. Some of them did turn out to be something other than galaxies. One of the original 6 universe breakers, when examined more closely, appeared to be a quasar. A quasar is what you get when a supermassive black hole is actively feeding on gas and matter, producing an incredibly bright beam of energy. Quasars can outshine entire galaxies, and they can be easily mistaken for massive galaxies if you are not careful. But even accounting for quasars and other sources of confusion, there were still way too many massive objects in the early universe. The problem was not going away. If anything, it was getting bigger. And then scientists started noticing something else. Something that would add an entirely new layer of mystery to the puzzle. Among all these red dots in the ancient universe, some were different from the others. They were smaller, more compact. and they had very strange properties that did not match any known type of object. Scientists started calling these objects little red dots. It was an informal name, but it stuck. And these little red dots would turn out to be one of the most surprising discoveries JWST has ever made. Between 2023 and 2025, JWST identified over 300 of these little red dots. They appear to have existed mostly between 600 million and 1.6 billion years after the Big Bang. They are extremely difficult to observe, even for the most powerful telescope ever built. As one researcher described it, they are at the limits of JWST's observational capability. When scientists analyzed the light from these little red dots, they found something strange. About 80% of them showed very broad emission lines. Now, without getting too technical, emission lines are like the fingerprints we talked about earlier. They tell you what elements are present in an object and how those elements are behaving. Broad emission lines typically mean that the material emitting the light is moving very fast. And the kind of speed scientists were seeing in these little red dots could only be explained by one thing: supermassive black holes. Here is what that means. These compact little objects appear to have enormous black holes at their centers. Black holes that are actively feeding on surrounding gas and matter. Black holes that are millions of times more massive than our Sun. But that creates another impossible problem. Because according to our understanding of how black holes form, there simply was not enough time for black holes this massive to exist so early in the universe. Let me explain. Normal black holes form when massive stars die. A star has to live its entire life, burning through its nuclear fuel over millions or even billions of years, before it can collapse into a black hole. And that black hole starts out relatively small. To grow into a supermassive black hole with millions of solar masses, it has to gradually feed on gas and matter over extremely long periods of time. There is a speed limit on how fast a black hole can grow. It is called the Eddington limit. When a black hole feeds too aggressively, the energy it releases pushes away the very material it is trying to consume. It is like trying to drink from a fire hose. The pressure of the water pushes you away before you can swallow anything. So according to standard physics, there was no way for black holes to grow to supermassive sizes in just a few 100 million years. The universe was not old enough. The math simply did not work. Yet there they were, little red dots with massive black holes, existing at a time when those black holes should have been impossible. Something was very, very wrong with our understanding of the early universe. Scientists started calling this the impossible black hole problem, and it added a whole new dimension to the mystery. The universe breaker galaxies were already challenging our models. Now the little red dots were showing us that not just galaxies, but also black holes, had somehow grown much faster than physics said they should. It was as if the early universe was operating under different rules. Rules we did not understand. So what is actually going on here? How can these massive galaxies and supermassive black holes exist when our best theories say they should not? Scientists have been working around the clock to figure that out, and they have come up with several possible explanations. The first possibility is that we have been wrong about how efficiently stars can form. In the modern universe, star formation is actually pretty inefficient. When a cloud of gas collapses to form new stars, only about 10 to 20% of the gas actually turns into stars. The rest gets blown away by radiation pressure, stellar winds, and supernova explosions. But what if the early universe was different? What if conditions in those first few 100 million years allowed for much more efficient star formation? Some scientists have proposed what they call feedback-free models. The idea is that in the very early universe, before there were many heavy elements and before feedback processes had fully developed, gas might have converted into stars much more rapidly. Instead of 10 or 20% efficiency, maybe it was 50% or 80% or even higher. If early galaxies could convert almost all of their gas into stars, they could have grown much faster than our models predict. This would not require any new physics. It would just mean that conditions in the early universe were more favorable for rapid star formation than we realized. The second possibility involves supermassive black holes. In 2024, a team led by Joseph Silk, a famous cosmologist at Johns Hopkins University, proposed a radical idea. What if supermassive black holes did not come after galaxies, but before them? In the standard picture, galaxies form first, and then black holes grow gradually at their centers. But Silk and his colleagues suggested that maybe it was the other way around. Maybe massive black holes, formed very early, perhaps through exotic processes we do not fully understand, and then those black holes actually helped create galaxies around them. Here is how it would work. When a black hole feeds on gas, it does not just swallow everything quietly. It releases tremendous amounts of energy in the form of jets and outflows. This energy can actually compress nearby gas clouds, triggering them to collapse and form stars. So instead of black holes growing slowly inside existing galaxies, maybe black holes were there first, acting like cosmic factories that drove the rapid formation of stars and galaxies around them. This theory is still controversial, but it would explain why we see such massive black holes and such massive galaxies so early in the universe. They grew together, feeding off each other in a process that was much faster than what we see in the universe today. The third possibility is even more exotic. It involves something called primordial black holes. Most black holes form from dying stars, but there might be another kind of black hole that formed in a completely different way, in the first moments after the Big Bang itself. In the very early universe, just fractions of a second after the Big Bang, space was filled with hot, dense matter. In some places, that matter might have been packed so tightly that it collapsed directly into black holes, without ever forming stars first. These primordial black holes could have any size, from microscopic to massive. And if they existed, they would have been around from the very beginning of time. They would not need millions or billions of years to form like regular black holes do. Some scientists have suggested that primordial black holes could have served as seeds around which the first galaxies formed. Instead of waiting for dark matter halos to slowly accumulate mass, galaxies could have nucleated rapidly around these pre-existing black holes. If this theory is correct, it would solve a lot of problems. It would explain where the supermassive black holes came from. It would explain why galaxies grew so quickly. And it would fit with what JWST is actually seeing in the early universe. But there is a catch. We have no direct evidence that primordial black holes exist. They are purely theoretical at this point. Finding proof of their existence would be a Nobel Prize-worthy discovery. The fourth possibility is that some of what JWST is seeing is not actually galaxies at all. Remember, when you look at objects 13 billion light-years away, you do not see crisp, clear images. You see fuzzy blobs, smudges of light. And interpreting those smudges requires making assumptions about what you are looking at. What if some of these universe breakers are not massive galaxies full of stars? What if they are something else entirely? One alternative is that they could be quasars, the extremely bright regions around feeding supermassive black holes. Quasars can be so luminous that they outshine their entire host galaxy. If you are looking at a quasar from 13 billion light-years away, You might mistake it for a massive galaxy when it is actually just an incredibly bright black hole. Another alternative is something scientists have recently started calling black hole stars. This is a completely new concept that emerged from analyzing the little red dots. In 2024, researchers studying an extremely unusual little red dot nicknamed the Cliff proposed that these objects might represent a never-before-seen class of cosmic object. They suggest that these could be supermassive black holes that are feeding so rapidly and so intensely that they light up the dense cocoon of gas surrounding them. The gas around the black hole would glow like a star, making the whole object appear much more massive than it actually is. If black hole stars are real, they could explain a lot of what JWST is seeing. They would not require impossible amounts of stars or impossible amounts of mass. They would just be a new phenomenon that we have never observed before, because no telescope was powerful enough to see them until now. The fifth and most unsettling possibility is that there might be something fundamentally wrong with our models of cosmology. The Lambda CDM model has been incredibly successful at explaining the universe, but it is based on assumptions. Assumptions about how dark matter behaves. Assumptions about how dark energy works. Assumptions about the initial conditions of the universe. What if some of those assumptions are wrong? What if the Big Bang did not happen exactly the way we think it did? What if the universe is older than we believe? What if there are forces and processes at work that we have not yet discovered? Brr. If the universe breaker galaxies cannot be explained by any modification to our existing models, then we might need to consider more radical possibilities. We might need to rethink some of the most fundamental principles of cosmology. This is the option that scientists find most troubling, because it would mean that decades of work might need to be revised. But it is also the option that could lead to the biggest breakthroughs. Scientific revolutions happen when existing theories fail to explain new observations. And right now, our theories are struggling. So which explanation is correct? The honest answer is that we do not know yet, and that is actually a good thing. Science thrives on mysteries. It advances when observations challenge existing theories and force us to think in new ways. What we do know is that the early universe was not what we expected. It was stranger, more active, and more dynamic than our models predicted. Massive galaxies formed faster than they should have. Supermassive black holes appeared when they should not have existed. And the whole picture of cosmic evolution is now in question. But here is where I want to shift the tone of this story. Because what we have discussed so far might seem like a crisis. It might seem like JWST has broken astronomy and left scientists scrambling to pick up the pieces. But that is not really what is happening. Yes, the discoveries are surprising. Yes, they challenge existing models. But scientists are not panicking. They are excited. Think about what it means to discover something truly unexpected. It means there is more to learn. It means there are new frontiers to explore. It means the universe is more interesting and more mysterious than we thought. Erica Nelson captured this perfectly when she said, "The most exciting discoveries are definitely the ones you do not expect." She did not say the most troubling discoveries or the most disturbing discoveries. She said the most exciting ones. When scientists find something that does not fit their models, they do not throw up their hands in despair. They get to work. They gather more data. They develop new theories. They test those theories against observations. And slowly, step by step, they build a better understanding of the universe. That is exactly what is happening right now with the universe breakers and the little red dots. Since the initial discoveries in 2023, scientists have been conducting follow-up observations. They have been using JWST spectrograph To get detailed measurements of these mysterious objects, they have been comparing JWST data with observations from other telescopes, and they have been running new computer simulations to see if modified versions of existing models can explain what they are seeing. In 2024, a team of researchers used data from both Hubble and JWST to cross-check the findings. They looked at galaxies in the same era of the universe that both telescopes could observe. And what they found was actually encouraging. The Hubble data suggested that the amount of dark matter and the overall structure of the early universe was pretty much what the models predicted. The problem was not with cosmology as a whole. The problem seemed to be more specific to how galaxies and black holes formed within that structure. This is an important distinction. It means we probably do not need to throw out everything we know about the universe. We just need to refine our understanding of certain processes. We need better models for how stars formed in the early universe. We need better models for how black holes grew so quickly. We need to account for conditions and phenomena that we had not considered before. As one scientist put it, so far, it seems everything can still be explained with our cosmological model and our understanding of when the Big Bang happened. It just needs some fine-tuning. Fine-tuning is a much less scary phrase than breaking cosmology. It suggests that we are on the right track, but some of the details need adjustment. That is normal in science. That is how progress works. Let me give you an analogy. Imagine you have a map of a city that you have never visited. The map shows the major streets, the landmarks, the general layout. When you actually visit the city, you might find that some of the side streets are in slightly different positions than the map shows. You might discover alleyways and shortcuts that are not on the map at all. You might find that some buildings have been torn down and new ones have been built. Does that mean the map is useless? No. The map still gives you the big picture. The main streets are still where they should be. The landmarks are still accurate. You just need to update the details as you learn more. That is what is happening with our model of the universe. The big picture is probably still correct. The Big Bang happened. The universe expanded and cooled. Galaxies formed inside dark matter halos. All of that is almost certainly true. We just need to update our understanding of some of the details, especially when it comes to the very early universe. And JWST is giving us the information we need to make those updates. Every new observation provides another piece of the puzzle. Every spectrum reveals more about what these mysterious objects are made of and how they behave. Every analysis brings us closer to understanding what really happened in the first billion years of cosmic history. There is also something philosophically profound about all of this. We are not just learning about distant galaxies. We are learning about our own origins. Everything that exists today, including you and me, is made of atoms that were forged in the hearts of stars. Those stars were born in galaxies. Those galaxies formed in the early universe through processes we are only beginning to understand. When we look at the universe breakers and the little red dots, we are looking at the cosmic nurseries where the first generations of stars were born. Those stars created the elements that would eventually become planets, oceans, and living things. In a very real sense, we are looking at our own distant ancestors. Understanding the early universe is not just an abstract scientific exercise. It is a quest to understand where we came from and how the raw materials of life were created. JWST has opened a window into that distant past that was never possible before. And what we are seeing through that window is challenging us to think bigger, question our assumptions, and push the boundaries of human knowledge. The universe, it turns out, does not owe us an explanation. It does not have to fit neatly into our models and theories. It simply is what it is. And our job, as curious beings trying to make sense of our place in the cosmos, is to observe, learn, and adapt our understanding accordingly. The universe breakers are not breaking the universe. They are breaking our preconceptions about the universe. And that is a very different thing. Joel Leger said something that I think captures the spirit of this entire adventure. He said, "We have found something we never thought to ask the universe, and it happened way faster than I thought, but here we are." Here we are indeed, standing on the edge of a new era in cosmology, looking back across 13 billion years of cosmic history, seeing things that no human eye has ever seen, and asking questions that might reshape our understanding of everything. That is the beauty of science. It never ends. There is always another discovery to make, another mystery to solve, another frontier to explore. And right now, the James Webb Space Telescope is leading us into territory that no one imagined we would reach so quickly. The little red dots, the universe breakers, the impossible black holes. These are not problems to be feared. They are opportunities to be embraced. They are invitations to learn something new about the cosmos and about ourselves. So what happens next? As of right now, scientists are continuing to study these mysterious objects. More observations are being made. More data is being analyzed. New theories are being developed and tested. The scientific process is grinding forward, as it always does, slowly revealing the truth about our universe. In the coming years, we will learn more about whether the universe breakers are really as massive as they appear, or whether some of them are quasars or other objects masquerading as galaxies. We will learn more about the little red dots and whether they really contain supermassive black holes that formed impossibly fast. We will learn whether primordial black holes exist and whether they played a role in shaping the early universe. We will learn things that nobody has predicted. That is the nature of exploration. When you venture into unknown territory, you never know what you will find. And that is the most exciting part of all. The universe is vast beyond comprehension. It contains wonders we have not yet imagined. And for the first time in human history, we have a telescope powerful enough to reveal some of those wonders. What the James Webb Space Telescope has shown us is that the cosmos is stranger and more fascinating than we ever knew. The early universe was not a quiet, simple place where baby galaxies slowly grew over billions of years. It was a dynamic, active environment where massive structures formed with astonishing speed. How that happened is still a mystery. But mysteries are what drive science forward. They are what keep researchers working late into the night, analyzing data and developing theories. They are what inspire the next generation of astronomers and physicists. Somewhere out there, in a classroom or a backyard or a bedroom, a young person is looking up at the stars and wondering how it all began. And the discoveries being made right now by JWST might be the spark that ignites their curiosity and sets them on a path to becoming the scientist who finally solves the puzzle. That is how science works. Each generation builds on the work of those who came before. Each discovery opens new doors and raises new questions. And slowly, piece by piece, we assemble a picture of the universe that is ever more complete and ever more beautiful. The universe breakers remind us that there is still so much we do not know. They humble us, they challenge us, and they inspire us to keep looking, keep questioning, and keep pushing the boundaries of what is possible. When Erica Nelson first saw those fuzzy red dots in the JWST images, she called her girlfriend over and said, "This might be the most distant starlight we have ever seen." Think about the wonder in that moment, the thrill of discovery, the realization that you are seeing something no human being has ever witnessed. That is what makes astronomy special. It connects us to the infinite. It reminds us that we are part of something much larger than ourselves, and it shows us that even after thousands of years of watching the sky, there are still surprises waiting to be found. The James Webb Space Telescope has given us a gift. It has shown us the universe as we have never seen it before. It has challenged our theories and expanded our horizons. It has proven, once again, that the cosmos is stranger and more wonderful than we could have imagined, and it has reminded us of a fundamental truth. We are explorers. It is in our nature to seek out the unknown, to ask questions, and to push beyond the limits of our understanding. The universe may be full of mysteries, but mysteries are just opportunities waiting to be seized. The universe breakers exist, they are real, and they are teaching us something important about the cosmos we call home. Whether they turn out to be massive galaxies that form through processes we do not yet understand, or quasars powered by black holes that grew impossibly fast, or something else entirely that no one has imagined, they are expanding our knowledge and challenging our assumptions. And that is exactly what science is supposed to do. So the next time you look up at the night sky, remember what is out there. Remember that the light reaching your eyes has traveled for years, centuries, even millennia before arriving at this moment. Remember that behind that light are stories of cosmic evolution, stretching back nearly 14 billion years. And remember that somewhere out there, in the depths of the ancient universe, objects exist that should not be possible. Objects that are forcing us to rewrite the textbooks and rethink everything we thought we knew. The universe is not broken. Our understanding of it is just being updated. And that is a very exciting time to be alive. What do you think? Are we looking at a flaw in our math, or something truly alien to our universe? Let us know in the comments below. Thank you for joining us on this journey to the edge of the known cosmos. If you enjoyed this exploration of the universe breakers and the mysteries of the early universe, please like this video and subscribe to Cosmic Drift, and hit that notification bell so you do not miss our next deep dive into the wonders of space. Until next time, keep looking up. The universe has more secrets to reveal, and we are just getting started. But before we end, let me take you deeper into this story, because what we have covered so far is just the beginning. There are layers to this mystery that make it even more fascinating, and I want to share them with you. Let us go back to the very beginning. Not the beginning of the universe breaker story, but the beginning of everything. The Big Bang itself. Nearly 14 billion years ago, everything that exists today was compressed into a point smaller than an atom. All the matter, all the energy, all of space and time itself. Everything was there, packed into an unimaginably hot and dense singularity, and then it exploded. Actually, exploded is not quite the right word. It was not an explosion in the normal sense, like a bomb going off in empty space. There was no empty space for it to explode into. Space itself was created in that moment. The Big Bang was the birth of space and time together. In the first tiny fraction of a second, the universe went through a period called inflation. It expanded faster than the speed of light, doubling in size over and over again in an impossibly short time. By the time inflation ended, the universe had grown from something smaller than a proton to something larger than the observable universe is today. After inflation, the universe was filled with a hot, dense soup of particles and energy. It was so hot that atoms could not exist. Electrons and protons bounced around freely, constantly interacting with photons of light. The universe was opaque, like a thick fog that light could not penetrate. But as the universe expanded, it cooled, and about 380,000 years after the Big Bang, something remarkable happened. The temperature dropped to about 3,000 degrees, cool enough for the first stable atoms to form. Electrons finally bonded with protons to create hydrogen atoms. This moment is called recombination, and it changed everything. Once atoms formed, photons could finally travel freely through space. The fog lifted. The universe became transparent for the first time. Those photons are still traveling today. We can detect them with special instruments, and we call them the cosmic microwave background radiation, or CMB for short. Masin. It is the oldest light in the universe, a snapshot of what the cosmos looked like when it was just 380,000 years old. Scientists have studied the CMB extensively. They have mapped it across the entire sky, measuring its temperature in every direction. And what they found is remarkable. The CMB is almost perfectly uniform. No matter where you look, it has almost exactly the same temperature, about 2.7 degrees above absolute zero. But not perfectly uniform. There are tiny fluctuations, variations of about 1 part in 100,000. These fluctuations are incredibly important. They represent slight differences in density in the early universe, places where matter was just a little bit more concentrated than average. Those tiny fluctuations are the seeds of everything we see today. The slightly denser regions had slightly stronger gravity, which attracted more matter over time. Eventually, those regions collapsed to form the first stars and galaxies. It is one of the most beautiful things in all of science. The galaxies we see today, including our own Milky Way, grew from fluctuations that were imprinted in the cosmic microwave background billions of years ago. The pattern of the CMB predicted where galaxies would form long before they actually existed. And here is where the universe breakers become even more puzzling. The CMB gives us a very detailed picture of what the early universe was like. It tells us how much dark matter there was, how much ordinary matter, and how those fluctuations were distributed. And when scientists use that information to run computer simulations of how the universe evolved, they get results that match what we see today remarkably well. The simulations show dark matter slowly clumping together into halos. They show ordinary matter falling into those halos and gradually forming stars. They show small galaxies merging to form larger ones over billions of years. The simulations match the real universe almost perfectly, except for those first billion years. When JWST looked back to that early era, it found things the simulations did not predict. Massive galaxies where there should have been small ones. Supermassive black holes where there should not have been any at all. A universe that was far more developed than our models said it should be. It is like having a weather forecast that perfectly predicts today's weather, tomorrow's weather, and next week's weather, but completely fails to predict what happened yesterday. The models work great for most of cosmic history, but they seem to break down at the very beginning. This is deeply puzzling. It suggests that something happened in those first few 100 million years that we do not understand. Some process or condition that allowed galaxies and black holes to form much faster than our models predict. Let me tell you more about what we think might have been different about the early universe. One big difference is the composition of matter. In the universe today, stars are made from a mix of elements. Hydrogen and helium are the most common, but there are also significant amounts of heavier elements like carbon, oxygen, nitrogen, and iron. These heavier elements are called metals in astronomy, even though some of them are not metals in the chemistry sense. Metals are important for star formation. They help gas clouds cool down, which allows them to collapse more easily. they also affect how stars live and die. Metal-rich stars tend to be smaller and longer-lived than metal-poor stars. But in the early universe, there were no metals. The Big Bang only produced hydrogen, helium, and tiny amounts of lithium. That is it. All the heavier elements had to be created later, inside stars, through the process of nuclear fusion. The very first stars, the ones that formed from pure hydrogen and helium, must have been different from the stars we see today. Without metals to help the gas cool, these primordial stars could only form under certain conditions, and the stars that formed were probably massive, really massive, hundreds of times the mass of our Sun. Stars that big do not live long. They burn through their nuclear fuel in just a few million years, compared to the billions of years that smaller stars like our Sun can last. And when they die, they do not go quietly. They explode as supernovas, some of the most violent events in the universe. These early supernovas were crucial. They were the forges where the first heavy elements were created: carbon, oxygen, iron, gold. All of these elements were born in the nuclear inferno of dying primordial stars. And when those stars exploded, they scattered their newly created elements across space. The next generation of stars formed from gas that was now enriched with metals. These second-generation stars could be smaller and more varied than the first, and when they died, they added even more metals to the cosmic mix. This process continued generation after generation. Each new batch of stars created more heavy elements and scattered them into space. Over billions of years, the universe became enriched with the full periodic table of elements that we know today. But here is the thing. This enrichment process takes time. You need multiple generations of stars to live and die before the universe accumulates significant amounts of metals. And that means the very early universe, in those first few 100 million years, was almost completely metal-free. Scientists call this the epoch of the first stars, or sometimes the cosmic dawn. It is one of the most mysterious periods in cosmic history because we have never been able to see it directly. Until JWST. JWST was specifically designed to observe the cosmic dawn. Its infrared sensors are tuned to detect light from the era when the first stars and galaxies were forming. And what it is finding is challenging our assumptions about what that era was like. If the first stars were truly massive and short-lived, they should have gone through multiple generations very quickly. Each generation would have enriched the surrounding gas with metals. This could have accelerated the formation of smaller, more normal stars. It is also possible that the first stars were even more massive than we thought. There is a theoretical type of star called a supermassive star, which could be thousands or even tens of thousands of times the mass of our Sun. If stars this big actually existed in the early universe, they could have had dramatic effects on their surroundings. When a supermassive star dies, it might not explode as a supernova. Instead, it might collapse directly into a black hole without ejecting much material. This is called a direct collapse black hole, and it could provide a shortcut to creating massive black holes without having to grow them slowly over time. If early supermassive stars collapsed into black holes with masses of tens of thousands or even hundreds of thousands of solar masses, those black holes would have had a huge head start. They would not need to grow from small stellar mass black holes through billions of years of feeding. They would already be massive from the moment they formed. This is one possible explanation for the impossible black holes that JWST is finding. Maybe they did not grow from small seeds. Maybe they were born big. But there is another possibility that is even more intriguing. What if some of those black holes did not form from stars at all? Remember primordial black holes? The ones that might have formed directly from dense regions in the early universe, just fractions of a second after the Big Bang. These hypothetical objects have been debated for decades, but there has never been solid evidence that they exist. The JWST observations might be changing that. If primordial black holes exist, they could have served as seeds around which the first galaxies formed. Instead of waiting for dark matter to slowly accumulate into halos, galaxies could have nucleated rapidly around these pre-existing black holes. This would explain several puzzles at once. It would explain why we see such massive black holes so early. It would explain why some galaxies seem to have formed impossibly fast. And it would provide a new understanding of how structure in the universe developed. There is a group of scientists who have been studying this possibility in detail. They analyze the little red dots and the universe breakers, looking for signatures that might indicate primordial black holes. The research is ongoing, and the results are not yet conclusive, but the possibility is tantalizing. If primordial black holes are confirmed to exist, it would be one of the most important discoveries in cosmology. It would tell us something profound about the conditions in the universe just moments after the Big Bang. And it might even shed light on the nature of dark matter, since primordial black holes are one possible explanation for what dark matter might be. Let me talk more about dark matter, because it is central to this whole story. We cannot see dark matter. It does not emit light. It does not absorb light. It does not interact with ordinary matter except through gravity. For all practical purposes, it is invisible, but we know dark matter exists because we can see its effects. Galaxies rotate faster than they should based on the amount of visible matter they contain. The only way to explain their rotation is to assume there is additional mass that we cannot see. That invisible mass is dark matter. Dark matter makes up about 27% of the universe's total mass and energy. Ordinary matter, the stuff that makes stars, planets, and people, is only about 5%. The rest is dark energy, but that is a topic for another video. In the standard model of cosmology, dark matter plays a crucial role in galaxy formation. Because dark matter only interacts through gravity, it was able to start clumping together before ordinary matter could. While ordinary matter was still bouncing around as hot plasma, dark matter was quietly accumulating into structures called halos. These dark matter halos provided the gravitational scaffolding for galaxies. Ordinary matter fell into the halos and collected at their centers. Eventually, that matter formed stars, and those stars became the visible parts of galaxies that we can observe. But here is the thing. If this picture is correct, the first galaxies should have formed inside the first dark matter halos. And the first halos were small. It takes time for gravity to build up larger and larger structures. So the first galaxies should have been small too. The universe breakers challenge this picture. They are too massive for the dark matter halos that should have existed at that time. Either our understanding of how dark matter halos form is wrong, or there is some other mechanism at work that we have not considered. One possibility is that we are wrong about the properties of dark matter itself. The standard assumption is that dark matter is cold, meaning the particles move slowly compared to the speed of light. Cold dark matter clumps efficiently on small scales, which is consistent with the structure we see in the universe today. But what if dark matter has different properties than we assume? What if it is warmer, or has self-interactions, or behaves differently in the early universe than it does today? These alternative dark matter models are being explored by theorists, and JWST observations are providing new data to test them against. Another possibility is that baryonic physics, the behavior of ordinary matter, is different in the early universe than we assumed. Maybe gas was able to cool and collapse more efficiently in those first few 100 million years. Maybe star formation was more vigorous. Maybe feedback processes, like supernova explosions blowing gas out of galaxies, were weaker. These are all active areas of research. Scientists are running new simulations that incorporate different assumptions about the early universe. They are looking for combinations of parameters that can reproduce what JWST is seeing. So far, none of the models work perfectly, but progress is being made. Let me tell you about one particularly interesting idea that has emerged from the study of little red dots. In late 2024, a team of researchers analyzed a particularly extreme little red dot that they nicknamed the cliff. The name comes from a feature in its spectrum, a sudden sharp rise in brightness at certain wavelengths. When the team tried to explain the cliff using standard models, they failed. It did not look like a normal galaxy. It did not look like a normal quasar. It did not match any known type of object. So they proposed something new. They called it a black hole star. The idea is this. Imagine a massive black hole that is feeding extremely rapidly on surrounding gas, so rapidly that it is pushing against the limits of physics. The gas around the black hole forms a dense, turbulent cocoon that is heated to extreme temperatures. This cocoon glows brightly, like the atmosphere of a star. From a great distance, this black hole star would look like a compact, bright red object, exactly like a little red dot. Black hole stars would represent a phase of cosmic evolution that we have never observed before. They would be intermediate objects, somewhere between naked black holes and full-fledged galaxies. And they might be the key to understanding how supermassive black holes grew so quickly in the early universe. If a black hole can enter this black hole star phase, it could grow much faster than normal physics allows. The dense gas cocoon would shield the black hole from its own radiation, allowing it to feed continuously without the usual feedback effects that slow down growth. Once the black hole has consumed most of the available gas, the cocoon would dissipate and the black hole would emerge. At that point, it would look like a normal supermassive black hole at the center of a galaxy. This theory is still new and highly speculative, but it is exactly the kind of creative thinking that the JWST observations demand. When the data does not fit existing theories, scientists have to develop new ones. And sometimes those new theories turn out to be correct. Let me take a step back and talk about what this all means for our understanding of the universe. For most of human history, we had no idea how big the universe was or how old it might be. People looked up at the stars and saw points of light, but they did not know what those lights were or how far away they might be. Just a century ago, astronomers were still debating whether the Milky Way was the entire universe or just one galaxy among many. It was not until Edwin Hubble observed distant galaxies in the 1920s that we realized the universe was vastly larger than anyone had imagined. And it was not until the discovery of the cosmic microwave background in 1965 that we had solid evidence for the Big Bang. Before that, some scientists believed the universe might be eternal, with no beginning and no end. In the decades since, we have built up an incredibly detailed picture of cosmic history. We know when the Big Bang happened to within a few 100 million years. We know how the elements were formed. We know how galaxies evolved over billions of years. We can trace the expansion of the universe from the first moments to the present day. The Lambda CDM model represents the culmination of all this work. It is the best model we have ever had for how the universe works. It explains an enormous range of observations from the cosmic microwave background to the distribution of galaxies to the acceleration of cosmic expansion. And now JWST is testing that model in ways that were never possible before. When scientists look at the universe breakers and the little red dots, they are not just studying distant objects, they are testing the foundations of cosmology. Every observation either confirms or challenges our understanding of how the universe works. So far, the observations are mostly confirming the big picture while challenging some of the details. The Big Bang still happened. The universe is still about 13.8 billion years old. Dark matter and dark energy still exist. Galaxies still formed inside dark matter halos. But the details of how the first galaxies formed are turning out to be more complicated than we thought. Star formation in the early universe might have been more efficient. Black holes might have formed through exotic processes we did not consider. The conditions in the first few 100 million years might have been quite different from what our models assumed. This is actually how science is supposed to work. You build the best model you can based on available evidence. Then you make new observations that test the model. When the observations reveal discrepancies, you refine the model to match reality better. The Lambda CDM model is not broken. It is being updated, and each update makes it more accurate and more complete. Let me tell you about some of the specific observations that are helping scientists refine their models. One important tool is spectroscopy. When scientists take a spectrum of a distant galaxy, they split its light into component wavelengths. This reveals a wealth of information about the galaxy's composition, temperature, and motion. Different elements produce different patterns in a spectrum. Hydrogen has its signature. Oxygen has its signature. Iron has its signature. By analyzing these patterns, scientists can determine what elements are present in a distant galaxy and in what abundances. For the universe breakers and little red dots, spectroscopy has been crucial. It has helped confirm that some of these objects really are as distant as they appear. It has revealed the presence of supermassive black holes in some of them, and it has provided clues about what these objects actually are. JWST's spectrograph, called NIRSpec, is one of the most powerful instruments ever built for studying distant galaxies. It can take spectra of hundreds of objects simultaneously, allowing scientists to survey large numbers of galaxies efficiently. Since JWST began operations, NIRSpec has provided spectra for thousands of distant objects. This data is being analyzed by teams around the world, and new discoveries are being announced regularly. Another important tool is gravitational lensing. This is a phenomenon predicted by Einstein's theory of general relativity. When light passes near a massive object, its path gets bent by gravity. If a massive galaxy or galaxy cluster sits between us and a more distant object, it can act like a giant magnifying glass, distorting and amplifying the light from behind. Gravitational lensing allows us to see objects that would otherwise be too faint to detect. By carefully analyzing lensed images, scientists can learn about both the foreground lens and the background source. Some of the most distant galaxies ever observed were found using gravitational lensing. The magnification provided by foreground galaxy clusters allowed JWST to see objects that would have been invisible otherwise. This technique is being used to study the little red dots and universe breakers. When one of these objects happens to lie behind a gravitational lens, scientists can get an enhanced view that reveals details that would otherwise be undetectable. Let me also mention something about the sheer scale of what we are discussing. The light from the universe breakers has been traveling for over 13 billion years to reach us. That is almost the entire age of the universe. That light left its source when the cosmos was young and hot, and mostly empty of galaxies. During those 13 billion years, the universe has changed beyond recognition. The first stars have lived and died countless times over. Galaxies have formed, merged, and evolved. Our own solar system has come into existence, a latecomer in cosmic history. When we look at the universe breakers, we are looking at a time before the sun existed, before the Earth existed, before life existed anywhere in the universe as far as we know. We are seeing the universe in its infancy, when everything was just beginning. And what we see is not what we expected. Instead of a quiet nursery of baby galaxies, we see a vibrant, active cosmos full of massive structures that formed with remarkable speed. This forces us to reconsider some basic assumptions about cosmic evolution. How quickly can galaxies grow? How efficiently can stars form? How fast can black holes accumulate mass? The answers to these questions are still being worked out. But one thing is clear. The universe is more dynamic and more capable of rapid change than we previously believed. Let me share some more details about the specific galaxies that have been observed. One of the most studied universe breakers has been given the designation Sears 93316. When it was first identified, its photometric redshift suggested it might be the most distant galaxy ever observed. If the measurement was correct, it would have existed just 235 million years after the Big Bang. At that distance, the galaxy would be so young that it pushes the limits of what is physically possible. There simply would not have been enough time for such a massive galaxy to form through normal processes. But when scientists obtained a spectrum of Sears 93316, they got a surprise. The spectroscopic redshift did not match the photometric estimate. The galaxy turned out to be much closer than originally thought, still very distant, but not record-breaking. This is an important cautionary tale. Photometric redshifts, which are based on colors alone, can sometimes be misleading. Spectroscopic confirmation is essential for accurately determining distances. Since then, scientists have been more careful about claiming record-breaking distances. They wait for spectroscopic confirmation before making definitive statements. This has led to more reliable measurements, even if some of the most exciting initial claims have been revised. Another interesting case is the galaxy nicknamed Maisie's Galaxy, named after the daughter of one of the researchers who studied it. This galaxy was confirmed to have a spectroscopic redshift of about 11.4, meaning its light has been traveling for about 13.4 billion years. It is one of the most distant galaxies ever confirmed. Maisie's galaxy is a window into the cosmic dawn. It existed when the universe was only about 400 million years old. Studying it can tell us about what conditions were like during that mysterious early era. Then there is the galaxy GN-Z11, which holds a special place in astronomical history. It was discovered by the Hubble Space Telescope before JWST launched, and for years it was the most distant galaxy ever confirmed. JWST has since studied GN-Z11 in much greater detail, revealing that it hosts an actively feeding supermassive black hole. These individual galaxies are like puzzle pieces. Each one tells us something about the early universe. Put them all together, and a picture emerges of a cosmos that was more complex and more active than we previously knew. Let me also talk about what this means for the search for life in the universe. One of the big questions in science is whether we are alone. Is Earth the only planet with life, or is life common throughout the cosmos? To answer this question, we need to understand how common the ingredients for life might be. We know that life on Earth is based on certain elements, primarily carbon, but also oxygen, nitrogen, hydrogen, and smaller amounts of other elements like phosphorus and sulfur. These elements are created in stars. Hydrogen was made in the Big Bang, but everything heavier came from stellar nucleosynthesis, the process of fusing lighter elements into heavier ones inside stars. The universe breakers and the early formation of massive galaxies have implications for this picture. If galaxies formed faster than we thought, and if stars lived and died in rapid succession in those early galaxies, then the heavier elements might have been created and dispersed earlier than we expected. This could mean that the ingredients for life were available earlier in cosmic history, which could mean that life itself might have originated earlier than we thought possible. Of course, having the right ingredients is not the same as having life. There are many other factors involved, including the formation of rocky planets, the presence of liquid water, and countless other conditions that we do not fully understand. But the JWST observations remind us that the universe has been busy since the very beginning. It did not wait billions of years to start building complex structures. The cosmos got to work immediately, creating stars and galaxies at a pace we did not anticipate. This suggests that the universe might be more fertile ground for complexity than we realized. If galaxies could form fast, maybe life could emerge fast too. This is speculative, of course, but it is one of the fascinating implications of what JWST is discovering. Let me tell you about some of the ongoing and future research that will help us understand the universe breakers better. JWST is just getting started. It has been operating for only a few years, and it has enough fuel to continue working for at least 2 decades. In that time, it will observe thousands more distant galaxies, providing an ever clearer picture of the early universe. Several large survey programs are underway. JADES, the JWST, Advanced Deep Extragalactic Survey, is mapping some of the deepest regions of space ever studied. SEERS, which provided the initial universe breaker discoveries, continues to analyze more and more data. UNCOVER is using gravitational lensing to study the most distant objects possible. Each of these programs is generating enormous amounts of data. Scientists are working overtime to analyze it all, looking for patterns and insights that will help us understand the early cosmos. At the same time, theorists are developing new models to explain the observations. They are running sophisticated computer simulations that test different assumptions about physics in the early universe. They are exploring exotic possibilities like primordial black holes and modified dark matter models. The next few years will be crucial for resolving some of the mysteries we have discussed. As more data comes in and more analysis is done, the picture will become clearer. Some of the current puzzles might be resolved. New puzzles will certainly emerge. There are also future telescopes being planned that will complement JWST's capabilities. The Nancy Grace Roman Space Telescope, scheduled to launch in the mid-2020s, will survey much larger areas of the sky than JWST can. While it will not see quite as faintly as JWST, it will observe many more objects, providing statistical power that JWST cannot match. On the ground, extremely large telescopes are being built in Chile and elsewhere. These giant instruments will have mirrors 25 to 40 meters across, dwarfing anything that has come before. While they cannot match JWST's infrared sensitivity, they can observe in other wavelengths and provide complementary data. Together, these telescopes will create a comprehensive picture of the universe that no single instrument could provide alone. Each one has strengths and weaknesses, but working together, they will push the boundaries of what we can know. I want to take a moment to appreciate the human story behind all of this. The James Webb Space Telescope was decades in the making. It was proposed in the 1990s, and construction began in the early 2000s. Thousands of engineers, scientists, and technicians worked on the project over more than 20 years. There were setbacks along the way, technical problems, budget overruns, schedule delays. At times, it seemed like the telescope might never be finished, but the teams persisted. They solved problem after problem. They tested and retested every component. They developed new technologies that did not exist when the project began, and on Christmas Day 2021, their work paid off. JWST launched from French Guiana on an Ariane 5 rocket, beginning its journey to a point in space 1 million miles from Earth. The launch was perfect. The deployment of the telescope's complex structures went flawlessly. Within months, JWST was producing scientific data that exceeded expectations. The people who built JWST did not know what it would find. They knew it would see further and more clearly than any telescope before it, but they could not have predicted the universe breakers, or the little red dots, or any of the other surprises that have emerged. That is the nature of exploration. You build the best tools you can, you send them into the unknown, and you see what comes back. The universe breakers are a testament to human curiosity and ingenuity. They exist because we wanted to know more about the cosmos than we could learn from the ground. We built an incredible machine, sent it into space, and it showed us things we never imagined. And now we get to grapple with what those discoveries mean. We get to revise our theories and develop new ideas. We get to push the boundaries of human knowledge. That is a privilege. Future generations will look back on this time as a turning point in our understanding of the universe. The discoveries being made today will appear in textbooks for centuries to come. Let me also acknowledge the uncertainties that remain. Science is not about having all the answers. It is about asking good questions and pursuing the truth wherever it leads. Right now, there are many questions about the early universe that we cannot answer with confidence. Are the universe breakers really as massive as they appear? Or are there systematic errors in our measurements that make them seem bigger than they are? Are the little red dots powered by supermassive black holes or by dense clusters of stars? Or are they something else entirely? Did primordial black holes exist? And did they play a role in seeding the first galaxies? What processes allowed stars and galaxies to form so quickly in the early universe? These are open questions. Scientists have hypotheses and theories, but we do not have definitive answers yet. That uncertainty is uncomfortable for some people. They want to know the truth, and they want to know it now. But uncertainty is part of the scientific process. It is what drives us to keep looking, keep measuring, keep testing. The questions we cannot answer today are the questions that motivate the research of tomorrow. And honestly, the uncertainty is part of what makes this exciting. If we already knew everything, there would be nothing left to discover. The fact that the universe can still surprise us, even after all these years of study, is wonderful. Let me close by returning to where we started. The James Webb Space Telescope has discovered galaxies that should not exist. Objects so old and so massive that they challenge our understanding of the cosmos. These universe breakers are not anomalies to be explained away. They are signals from the early universe, telling us that reality is more complex than our models predicted. Scientists are working hard to understand what these objects are and how they formed. New theories are being developed. New observations are being made. The mystery is being chipped away at, piece by piece. But even as answers emerge, new questions arise. That is the nature of science. Each discovery opens new doors and reveals new horizons. What we know for certain is this: the universe is stranger and more wonderful than we ever imagined. The early cosmos was not a quiet place, waiting for galaxies to slowly form. It was a dynamic, active environment where massive structures emerged with surprising speed. This challenges our theories. It forces us to think differently. It pushes us to expand our understanding. And that is exactly what science is supposed to do. The universe does not owe us simplicity. It does not have to fit neatly into our equations and models. Our job is to observe, learn, and adapt. The universe breakers are teaching us something important. They are showing us that we still have much to learn. And they are reminding us that the cosmos always has more secrets to reveal. As Joel Leger said, the universe is much weirder than we can imagine, and all we can do is follow its clues. So let us follow those clues. Let us keep watching, keep questioning, keep pushing the boundaries of knowledge. The universe has been waiting 13.8 billion years for someone to ask these questions. We are the generation that gets to pursue the answers. What do you think is causing these impossible galaxies? Is it faster star formation, primordial black holes, black hole stars, or something else entirely that nobody has thought of yet? Share your thoughts in the comments below. I want to hear your ideas about what might be happening in the early universe. And if you found this journey through cosmic history fascinating, please like this video and subscribe to Cosmic Drift. We explore the strangest and most wonderful mysteries of the universe, and there is so much more to discover together. Until next time, keep looking up. The universe has secrets to share, and we are just getting started uncovering them. Now let me take you even deeper into this cosmic mystery, because there are aspects of this story that deserve more attention, details that illuminate just how profound these discoveries really are. Let us talk about what it actually means to look back in time. When you gaze up at the night sky on a clear evening, you are not seeing the universe as it exists right now. You are seeing it as it existed in the past. The light from even the nearest stars takes years to reach your eyes. Consider Alpha Centauri, the closest star system to our Sun. It is about 4.3 light years away. That means the light you see from Alpha Centauri tonight left that star more than 4 years ago. If Alpha Centauri suddenly vanished right this moment, we would not know about it until 2029. Now extend that principle to greater distances. The Andromeda Galaxy, our nearest large galactic neighbor, is about 2.5 million light-years away. When you look at Andromeda, you are seeing it as it was 2.5 million years ago, when our ancestors were just beginning to walk upright on the African savanna. The further you look, the further back in time you see. Distant galaxies show us the universe as it was billions of years ago, and the universe breakers, those impossibly massive galaxies discovered by JWST, show us a time when the cosmos itself was a cosmic infant. This is why astronomers are so excited about JWST's capabilities. It is not just a powerful telescope. It is a time machine that lets us witness the birth of cosmic structures. Think about what it means to see light that has been traveling for 13 billion years. That light began its journey before our sun existed, before our solar system formed, before the atoms that make up your body were assembled in the hearts of long-dead stars. That ancient light has traveled through expanding space, past countless galaxies, through voids hundreds of millions of light-years across. It has survived for eons, red-shifted and dimmed by the stretching of space-time, but still carrying information about its origin. And now that light has landed on the golden mirrors of the James Webb Space Telescope, ending its 13 billion-year journey at last. From that faint signal, we can reconstruct what the early universe looked like. It is one of the most remarkable achievements in the history of science. Let me tell you more about what the early universe was actually like. In the first moments after the Big Bang, the universe was unimaginably hot. Temperatures were so extreme that matter as we know it could not exist. Particles and antiparticles popped in and out of existence in the seething quantum chaos. As the universe expanded, it cooled. After about 1 second, protons and neutrons formed. After about 3 minutes, some of these protons and neutrons fused together to form helium nuclei in a process called Big Bang nucleosynthesis. But the universe was still far too hot for atoms to form. Free electrons bounced around like pinballs, constantly colliding with protons and photons. Light could not travel far before being scattered. The universe was opaque, filled with a glowing fog of plasma. This continued for about 380,000 years. Then the temperature dropped to around 3,000 Kelvin, cool enough for electrons to combine with nuclei and form neutral atoms. This moment, called recombination, was when the cosmic fog lifted. Suddenly, photons could travel freely through space. The universe became transparent. Those photons from recombination are still traveling today, and we detect them as the cosmic microwave background. After recombination, the universe entered a period called the cosmic dark ages. There were no stars yet, no galaxies, just vast clouds of hydrogen and helium gas slowly collecting under the influence of gravity. The dark ages lasted for roughly 100 to 200 million years. During this time, the universe was literally dark. There were no sources of light except the fading glow of the cosmic microwave background, which had already cooled from visible light to infrared. Then something remarkable happened. The first stars ignited. These primordial stars were unlike anything that exists in the universe today. They formed from pure hydrogen and helium, with no heavier elements to help the gas cool. As a result, they were probably enormous, perhaps hundreds of times the mass of our Sun. These massive stars burned hot and bright. They produced intense ultraviolet radiation that began to ionize the surrounding hydrogen gas. Slowly, the universe lit up again as bubbles of ionized gas expanded around the first stars. This period is called the epoch of Reionization, and it lasted for several 100 million years. By about 1 billion years after the Big Bang, most of the hydrogen in the universe had been ionized again, and the cosmos was fully transparent to ultraviolet light. The epoch of Reionization is one of the most important but least understood periods in cosmic history. JWST was specifically designed to study this era, and the universe breakers and little red dots are providing crucial data. What is becoming clear is that Reionization may have happened faster and more unevenly than we thought. The presence of massive galaxies and supermassive black holes early in cosmic history suggests that the universe was more structured at that time than our models predicted. This has implications for understanding how the universe evolved. If ionizing radiation was produced more intensely and in more concentrated regions than we thought, the pattern of Reionization could have been quite different from what simulations show. Scientists are now revising their models of Reionization to account for the JWST observations. This is another example of how real data is forcing us to update our theoretical understanding. Let me describe more about the technical aspects of how JWST studies these distant objects. JWST has 4 main science instruments. Each one is designed for different types of observations, and together they provide a comprehensive toolkit for studying the cosmos. NIRCam, the near-infrared camera, is the telescope's primary imaging instrument. It takes pictures in wavelengths ranging from 0.6 to 5 microns, which covers the range where light from the earliest galaxies is detected. NIRCam provided the images in which the universe breakers were first identified. NIRSpec, the near-infrared spectrograph, splits light into its component wavelengths. This allows scientists to measure redshifts precisely and identify the chemical composition of distant objects. NIRSpec can take spectra of up to 100 objects simultaneously, making it incredibly efficient for surveys. MIRI, the mid-infrared instrument, sees longer wavelengths from 5 to 28 microns. These wavelengths are useful for studying cooler objects and for detecting certain molecules. MIRI operates at an even colder temperature than the rest of the telescope, just 7 Kelvin above absolute zero. FGS NIRIS is a combination fine guidance sensor and imager. It helps keep the telescope precisely pointed and also provides specialized imaging capabilities, including a mode that can detect exoplanet atmospheres. When studying the universe breakers, scientists use multiple instruments together. NIRCam images identify candidate objects and measure their colors. NIRSpec follow-up observations confirm distances and reveal physical properties. MIRI data can help distinguish between different types of objects and detect signs of dust. This multi-instrument approach is essential for understanding what these mysterious objects really are. A single image or measurement can be misleading, but when multiple lines of evidence point to the same conclusion, scientists can be more confident in their interpretation. Let me explain more about redshift and how it is measured. Redshift is one of the most important concepts in observational cosmology. It quantifies how much the wavelength of light has been stretched by the expansion of the universe. Astronomers denote redshift with the letter Z. If an object has a redshift of Z equals 1, that means its light has been stretched by a factor of 2. Wavelengths that were originally 500 nanometers are now 1000 nanometers, for example. For very distant objects, redshifts can be much higher. The universe breakers have redshifts of around 7 to 10, meaning their light has been stretched by factors of 8 to 11. Light that was originally ultraviolet or blue has shifted all the way to infrared. Photometric redshifts are estimated by measuring how bright an object appears in different color filters. Because light is shifted toward redder wavelengths, distant objects look different than nearby objects when viewed through multiple filters. By fitting the observed colors to model spectra, astronomers can estimate the redshift. Spectroscopic redshifts are measured directly from the spectrum of an object. Atoms emit and absorb light at very specific wavelengths, creating characteristic patterns in spectra. By identifying these patterns and seeing how much they have shifted from their normal positions, astronomers can determine the redshift precisely. Spectroscopic redshifts are more accurate than photometric redshifts, but they require more telescope time to obtain. For the faintest and most distant objects, getting a good spectrum can require hours of observation. The universe breaker discoveries initially relied on photometric redshifts. As we discussed earlier, some of those initial estimates turned out to be incorrect when spectroscopic follow-up was done. This underscores the importance of confirming distances with spectroscopy. Let me tell you about some specific features that astronomers look for in the spectra of distant galaxies. One important feature is the Lyman alpha line. This is a specific wavelength of ultraviolet light emitted by hydrogen atoms. When electrons in hydrogen atoms transition between energy levels, they emit or absorb photons at very precise wavelengths. The Lyman alpha transition produces light at 121.6 nanometers. For a galaxy at redshift 7, this Lyman alpha light would be shifted to about 974 nanometers, which is in the near-infrared range that JWST can detect. Finding this line in the spectrum confirms that the object is at high redshift and tells you exactly how high. Another important feature is the Balmer break. This is a sudden change in brightness at a specific wavelength caused by hydrogen absorption. The location and strength of the Balmer break can tell scientists about the age of the stellar population in a galaxy. For the little red dots, the Balmer break has been particularly interesting. Some of these objects show an unusually sharp Balmer break that is difficult to explain with normal stellar populations. This is one reason scientists have proposed alternative explanations like black hole stars. Emission lines from other elements are also important. Oxygen, nitrogen, and carbon all have characteristic lines that can be detected in galaxy spectra. The presence and strength of these lines reveal the chemical composition of the gas in distant galaxies. For the earliest galaxies, we expect to see less of these heavier elements because they had not yet been produced in large quantities. Measuring the metallicity of high redshift galaxies tells us about the history of star formation and chemical enrichment. Let me discuss the concept of stellar mass and how it is estimated. When we say the universe breakers contain as many stars as the Milky Way, how do we actually know that? We cannot count individual stars in galaxies billions of light years away. Even JWST cannot resolve them. Instead, astronomers estimate stellar mass from the total light a galaxy emits. More stars means more light. So brighter galaxies generally have more stellar mass, but it is not quite that simple. The relationship between light and mass depends on what kind of stars a galaxy contains. Young, massive stars are much brighter than old, low-mass stars. A galaxy dominated by young stars will appear brighter for its mass than a galaxy with older stars. To account for this, astronomers use models of stellar populations. They make assumptions about the mix of star ages and masses in a galaxy and calculate how much light that mix would produce. By comparing observed brightness to model predictions, they can estimate the total stellar mass. For the universe breakers, these estimates suggest masses of tens of billions of solar masses, comparable to large present-day galaxies. But there are uncertainties in the modeling that could affect these numbers. One concern is that some of the light might not come from stars at all. If a galaxy contains an active black hole, the accretion disk around that black hole can produce significant light. This could make the galaxy appear more massive than it really is, if that light is mistakenly attributed to stars. This is one reason the little red dots are so confusing. They emit a lot of light, but it is not clear how much comes from stars versus how much comes from black hole activity. Untangling these contributions requires careful analysis of the spectrum and other properties. Let me talk about the cosmic web and how galaxies are distributed throughout the universe. Galaxies are not scattered randomly through space. They are organized into a vast network called the cosmic web. This web consists of filaments and sheets of galaxies separated by enormous voids, where almost no galaxies are found. The structure of the cosmic web was determined by the initial fluctuations in the early universe, the same fluctuations we see imprinted in the cosmic microwave background. Regions that were slightly denser than average attracted more matter over time. Regions that were slightly less dense lost matter. Over billions of years, this process created the web-like structure we see today. In the standard picture, galaxies form where filaments of the cosmic web intersect. These are the densest regions where the most dark matter has accumulated. The largest galaxy clusters are found at the nodes of the web, where multiple filaments come together. The universe breakers challenge this picture somewhat. If massive galaxies existed just a few 100 million years after the Big Bang, did the cosmic web already have sufficient structure to host them? Or did these galaxies form through some process that did not require pre-existing web structure? These questions are still being investigated. Some scientists suggest that the universe breakers may be located at especially dense regions of the early web, places where structure formation was accelerated. Others propose that these galaxies formed through processes that are independent of the web structure. Understanding where the universe breakers fit into the cosmic web will require mapping the distribution of early galaxies in 3 dimensions. This is challenging because it requires redshifts for many galaxies in the same region of sky. But JWST's spectroscopic capabilities are making this possible. Let me describe some of the collaborative nature of this research. The discovery of the universe breakers was not the work of a single team. It involved researchers from universities and institutions around the world. The lead author of the original Nature paper was Ivo Labe from Swinburne University of Technology in Australia. Co-authors included scientists from the United States, Denmark, Spain, and other countries. This international collaboration is typical of modern astronomy. The data from JWST is made publicly available after a brief proprietary period, allowing scientists everywhere to analyze it. Different groups bring different expertise and perspectives, which leads to more robust conclusions. Competition also plays a role. When exciting data becomes available, multiple teams race to analyze it and publish their results. This can lead to some confusion when different groups reach different conclusions, but it also ensures that findings are thoroughly vetted. For the universe breakers, the initial excitement was tempered by healthy skepticism. Other scientists asked probing questions. Are the redshifts really accurate? Could instrumental effects be causing the strange colors? Are the mass estimates reliable? This skepticism is an essential part of science. Extraordinary claims require extraordinary evidence, and the universe breakers are certainly extraordinary claims. The ongoing process of questioning, testing, and verifying is what gives us confidence that the final conclusions are correct. Let me tell you about some of the surprises that emerged as more data came in. One surprise was the diversity of the universe breakers and little red dots. They are not all the same. Some appear to be genuine massive galaxies with huge numbers of stars. Others seem to be dominated by black hole activity. Still others might be something entirely new. This diversity suggests that the early universe was more varied than we expected. There was not just one pathway to forming massive structures. Multiple processes were at work, creating a menagerie of different objects. Another surprise was how compact many of these objects are. The stars in universe breakers appear to be packed much more densely than in present-day galaxies. If you were standing on a planet in one of these ancient galaxies, the night sky would be ablaze with thousands of times more stars than we see from Earth. This extreme density is puzzling. How did so many stars form in such a small space? Did something in the early universe favor compact, dense star formation? Or did these galaxies start out extended and somehow compress over time? A third surprise was the apparent maturity of some of these early galaxies. They do not look like chaotic, newly forming systems. Some show evidence of organized structure, even hints of spiral arms. This suggests that galaxy evolution proceeded much faster than we thought. All of these surprises point to the same conclusion. The early universe was more active, more diverse, and more capable of rapid change than our models predicted. Let me discuss the philosophical implications of these discoveries. For centuries, humans have wondered about our place in the universe. Are we special? Is Earth unique? Is there meaning in the vastness of space? The universe breakers do not directly answer these questions, but they do provide perspective. They show us that the universe has been building complex structures for almost its entire history. The cosmos did not wait. It got to work immediately, creating stars and galaxies at a pace that surprises us even today. This suggests that the universe is inherently creative. It tends toward complexity. Given energy and matter and the laws of physics, it generates structure spontaneously. If the universe naturally produces galaxies and stars, might it also naturally produce planets capable of supporting life? Might life itself be a natural outcome of cosmic evolution, rather than a rare accident? We do not know the answers to these questions yet, but the JWST discoveries remind us that the universe is full of surprises. What we thought we knew is constantly being revised, and the possibilities are much wider than we often assume. Let me also consider what these discoveries mean for the future of cosmology. We are living in a golden age of observational astronomy. JWST is just one of many powerful instruments that are transforming our view of the universe. Ground-based telescopes with adaptive optics can now achieve remarkable resolution. Radio telescopes spanning continents can image black holes at the centers of galaxies. Gravitational wave detectors can hear the space-time ripples from colliding black holes and neutron stars. Each of these tools provides a different window on the cosmos. Together, they give us a multi-dimensional view that was unimaginable just a few decades ago. The universe breakers and little red dots are being studied with all of these tools. JWST provides infrared images and spectra. Ground-based telescopes provide complementary visible light observations. Radio telescopes search for emission from coal gas and dust. Future X-ray observations might detect the high-energy emission from accreting black holes. By combining all of this data, scientists are building an increasingly complete picture of what these mysterious objects really are. The era of single-wavelength astronomy is over. Modern cosmology requires a synthesis of observations across the entire electromagnetic spectrum. Looking ahead, even more powerful instruments are on the horizon. The European Extremely Large Telescope, currently under construction in Chile, will have a primary mirror 39 meters across. That is more than 5 times larger than any existing optical telescope. It will be able to image distant galaxies in unprecedented detail and measure their spectra with exquisite precision. The Square Kilometre Array, a radio telescope being built in South Africa and Australia, will be the most sensitive radio instrument ever constructed. It will map the distribution of hydrogen gas throughout the universe, including during the epoch of Reionization. The Vera C. Rubin Observatory, also in Chile, will survey the entire visible sky repeatedly over 10 years. This will allow scientists to discover transient phenomena like supernovae and to track the motions of solar system objects. Future space missions are also being planned. NASA's Nancy Grace Roman Space Telescope will survey large areas of sky in infrared light, complementing JWST's deep but narrow observations. Proposed X-ray missions could detect emission from the earliest black holes. All of these instruments will contribute to our understanding of the early universe. The mysteries uncovered by JWST will be investigated in ever greater detail, and new mysteries will undoubtedly emerge. Let me share some of the debates that are currently happening in the scientific community. Not all scientists agree on how to interpret the JWST observations. Some believe that the universe breakers and little red dots can be explained within the existing lambda CDM framework, with some adjustments to assumptions about star formation and black hole growth. Others think more radical changes might be needed. They point out that the observations consistently find more massive objects at earlier times than models predict. A pattern of repeated surprises suggests that something fundamental might be missing from our understanding. This debate is healthy and productive. It pushes scientists to examine their assumptions carefully and to consider alternative explanations. Eventually, the accumulation of evidence will favor one interpretation over another. There is also debate about how to properly estimate the masses of these distant objects. Different assumptions about stellar populations, dust, and black hole contributions can lead to significantly different mass estimates. Getting this right is crucial for understanding how challenging the observations really are. Some scientists have suggested that systematic errors in the data reduction or calibration might be affecting the results. JWST is a new instrument, and understanding its quirks takes time. As more experience is gained, some of the initial puzzles might turn out to have prosaic explanations. But so far, the basic findings have held up under scrutiny. There really do appear to be more massive galaxies in the early universe than expected. The question is how much more, and what that implies for cosmology. Let me describe some of the theoretical work being done to explain the observations. Theorists are exploring a wide range of possibilities. Some are modifying the properties of dark matter in their models. Maybe dark matter clumps more efficiently on small scales than previously assumed. Or maybe there are interactions between dark matter particles that affect structure formation. Others are exploring different initial conditions for the universe. The fluctuations imprinted by inflation determine how structure grows. If those fluctuations had different properties on small scales, galaxy formation could have proceeded differently. Still others are investigating exotic physics in the early universe. Maybe there were additional sources of energy or matter that we have not accounted for. Maybe the laws of physics were subtly different in the first billion years. Most of these exotic ideas will probably turn out to be wrong. That is normal in science. You explore many possibilities and eventually converge on the correct explanation. The wrong ideas are not wasted effort. They help define the boundaries of what is possible and sharpen our understanding. Let me return to the human element of this story. Behind every data point and every discovery is a person. Someone who spent years learning the techniques of astronomy. Someone who sacrificed other paths in life to pursue the mysteries of the cosmos. Someone who experienced the thrill of seeing something no human had ever seen before. Erica Nelson described the moment of discovery as the most exciting of her scientific career. Joel Leisure talked about the frantic process of trying to find a mistake and failing. Ivo Labbé coordinated teams across multiple continents to analyze the data. These are not abstract scientists working in isolation. They are people who care deeply about understanding the universe. They debate and collaborate and sometimes disagree. They experience frustration when the data is confusing and elation when insights emerge. The universe breakers are a product of human curiosity and effort. Without the generations of scientists who built and refined the tools of astronomy, we would never have seen them. Without the engineers who built JWST to exacting specifications, the telescope would not work. Without the observers who pointed it at the right patches of sky, the data would not exist. Science is a collective human endeavor. It builds on the work of those who came before and creates foundations for those who will come after. The discoveries of today will enable the discoveries of tomorrow. And that is perhaps the most important lesson of the universe breakers. They remind us that there is always more to learn. No matter how much we think we understand, the universe can still surprise us, and those surprises drive progress. The cosmos does not give up its secrets easily. It requires patience, ingenuity, and persistence to extract understanding from observations. But the rewards are worth it. Each discovery brings us closer to knowing our place in the universe. We are made of the same atoms that were forged in the first stars. We are connected to the most distant galaxies by the same laws of physics. When we look at the universe breakers, we are looking at our own cosmic ancestry. Understanding the early universe is not just an academic exercise. It is an exploration of who we are and where we came from. It is the grandest story ever told, and we are privileged to be able to read a few more pages. So let the mystery of the universe breakers inspire you. Let it remind you that the cosmos is vast and strange and wonderful. Let it motivate you to ask questions and seek answers. The universe is waiting to be explored, and the best discoveries may still lie ahead. What do you think? Are we looking at a flaw in our math, or something truly alien to our universe? Let us know in the comments below. Feedback can suppress star formation by removing the gas that would otherwise form new stars. It acts as a self-regulating mechanism, preventing galaxies from converting all their gas into stars at once. But what if feedback was weaker in the early universe? What if the first generations of stars did not produce as much disruptive energy? Or what if the energy was radiated away more efficiently? In that case, star formation could have proceeded more rapidly, without the usual interruptions. Black holes also provide feedback. When gas falls onto a black hole, it heats up and releases energy. In extreme cases, this can drive powerful jets and winds that affect the entire galaxy. This is called active galactic nucleus feedback, and it is thought to play an important role in regulating the growth of massive galaxies. The relationship between black hole feedback and galaxy growth is complex. In some cases, feedback might actually enhance star formation by compressing gas clouds and triggering collapse. In other cases, it might suppress star formation by heating and dispersing the gas. Understanding how feedback operated in the early universe is crucial for explaining the universe breakers. If the balance between star formation and feedback was different then, it could explain why massive galaxies formed so quickly. Let me also discuss the role of mergers in galaxy growth. In the standard picture, large galaxies form through the hierarchical merger of smaller galaxies. Small galaxies form first, then they collide and combine to form larger ones. Over billions of years, this process builds up the massive galaxies we see today. Mergers are dramatic events. When two galaxies collide, their gas is compressed and heated, often triggering bursts of star formation. Their stars get scrambled into new configurations. If both galaxies have central black holes, those black holes eventually merge as well. Could the universe breakers have formed through unusually rapid mergers? Maybe the early universe had regions where many small galaxies formed close together and quickly combined into larger structures. This is plausible, but it has its own challenges. Mergers take time. Even after two galaxies start interacting, it can take hundreds of millions of years for them to fully combine. If the universe breakers formed by merging smaller galaxies, those smaller galaxies would have had to form, evolve, and merge all within the first 500 million years. That is a tight timeline. Some scientists have proposed that the early universe might have had conditions that accelerated mergers. Higher densities, different dark matter properties, or other factors might have brought galaxies together faster than in later epochs. This remains an active area of research. Simulations are being run to test whether accelerated merging can explain the universe breakers. The results so far are mixed. but the possibility has not been ruled out. Let me share more about the emotional journey that scientists experience when making discoveries like this. When you spend years working on understanding the universe, you develop expectations. You think you know what you are going to find when new data comes in. You have models and theories that make predictions, and you expect reality to confirm those predictions. When reality does not cooperate, it can be disorienting. The first reaction is often disbelief. There must be a mistake. The data must be wrong. The analysis must have an error. Joel Leger described this perfectly when he said his first thought was that they had made a mistake and would find it and move on with their lives. That is a natural reaction. Scientists are trained to be skeptical, especially of their own results. But when you look for the mistake and cannot find it, the disorientation turns to excitement. You realize you might be seeing something genuinely new, something that challenges existing understanding. That is when the real fun begins. Science advances through anomalies. When observations do not match predictions, it means there is something new to learn. The universe breakers are exactly this kind of anomaly. They are telling us that the early universe was different from what we expected. Figuring out how it was different is the challenge. It requires creativity, persistence, and a willingness to question assumptions. It requires collaboration between observers who gather data and theorists who develop explanations. It requires patience, because answers do not come quickly, but eventually answers do come. The history of science is full of examples where puzzling observations led to revolutionary new understanding. The anomalous orbit of Mercury led to general relativity. The ultraviolet catastrophe led to quantum mechanics. The cosmic microwave background confirmed the Big Bang. The universe breakers might be leading us to similar breakthroughs. We do not know yet what those breakthroughs will be, but the potential is exciting. Let me tell you about some of the broader implications of these discoveries for our understanding of physics. Cosmology is ultimately a branch of physics. The universe operates according to physical laws, and understanding those laws allows us to understand the cosmos. When cosmological observations do not match predictions, it might mean we need to revise our understanding of physics itself. The lambda CDM model is based on known physics plus two mysterious components, dark matter and dark energy. We do not know what dark matter is made of. We do not understand the nature of dark energy. These are two of the biggest unsolved problems in physics. The universe breakers might be providing clues about these mysteries. If they cannot be explained by adjusting astrophysical assumptions like star formation rates, then maybe we need to reconsider the properties of dark matter or dark energy. For example, if dark matter has weak self-interactions that we have not accounted for, it might clump differently on small scales. This could affect how quickly the first dark matter halos formed and how efficiently they captured gas. Or maybe dark energy behaved differently in the early universe than it does today. If the dark energy density varied over time, it could have affected the expansion rate and the growth of structure in ways our current models do not capture. These are speculative possibilities. Most physicists expect that the universe breakers will eventually be explained within the lambda CDM framework with refined astrophysics. But the possibility of more fundamental discoveries remains open. Let me discuss the concept of fine-tuning and why it is relevant here. In physics, fine-tuning refers to situations where the parameters of a theory must take very specific values to match observations. If small changes in those parameters would produce dramatically different predictions, the theory is said to be fine-tuned. Fine-tuning is not necessarily bad. sometimes nature really does operate within narrow parameter ranges. But when a theory requires extensive fine-tuning, it raises questions about whether we truly understand the underlying physics. The lambda CDM model requires some fine-tuning to match observations. The amount of dark matter, the properties of dark energy, and the initial fluctuations from inflation must all take specific values to produce a universe like the one we see. If explaining the universe breakers requires additional fine-tuning, piling on more special conditions and adjustments, it might suggest that something is missing from the model. A more complete theory might naturally explain the observations without requiring so many adjustments. This is why the universe breakers are generating so much interest. They are testing lambda CDM in a regime where its predictions are most uncertain. How the model performs will tell us a lot about whether it captures the essential physics of the universe. Let me take you through some of the key milestones in this ongoing story. In July 2022, NASA released the first images from JWST. These images were immediately stunning, showing unprecedented detail in familiar objects like nebulae and galaxy clusters. But they also contained hints of the surprises to come. Within weeks, astronomers began identifying high redshift candidates in the deep field images. Some of these candidates seemed impossibly bright and massive for their apparent distances. The initial reports were cautious, noting that confirmation would require spectroscopy. In February 2023, the Nature paper on the universe breakers was published. This marked the first major announcement of galaxies that seemed to challenge cosmological models. The paper generated worldwide media attention and sparked intense scientific debate. Throughout 2023 and 2024, follow-up observations provided more data. Some initial candidates were revised or reclassified, but the basic finding held up. There really were more massive galaxies in the early universe than models predicted. The discovery of the little red dots added another layer to the mystery. These compact objects with possible supermassive black holes presented their own puzzles that overlapped with, but were distinct from the universe breaker phenomenon. In late 2024 and 2025, new theoretical proposals emerged to explain the observations. The black hole star hypothesis was proposed to explain the extreme little red dots like the cliff. Modified star formation models were developed to account for rapid galaxy growth. As of now, the scientific community is still working to converge on a consensus explanation. Multiple hypotheses remain viable. New data continues to come in. The story is far from over. Let me reflect on what all of this means for the future of astronomy. We are living through a remarkable period in the history of science. The tools available to astronomers today would have seemed like science fiction just a few decades ago. And those tools are revealing a universe that is more complex and more surprising than we imagined. The James Webb Space Telescope is the flagship of this new era, but it is just one instrument among many. Together, the observatories of the 21st century are painting a picture of the cosmos with unprecedented clarity and depth. The discoveries being made today will shape astronomy for generations. Young scientists entering the field now will spend their careers building on what JWST has found. The questions being asked today will be answered, and those answers will generate new questions. This is the nature of scientific progress. Each discovery opens new doors. Each answer reveals new mysteries. The universe is inexhaustible, always offering more to learn. The universe breakers remind us of this truth. They remind us that no matter how much we think we know, nature can always surprise us. They remind us to stay humble, stay curious, and stay open to the unexpected. As we close this exploration of the impossible galaxies, let me leave you with a thought. Somewhere in the universe, 13 billion years ago, stars were forming in newborn galaxies. Those stars lived their brief lives and died in spectacular explosions. Their deaths scattered heavy elements into space, seeding the cosmos with the raw materials for planets and life. Billions of years later, some of those atoms found their way into a cloud of gas that collapsed to form our sun and solar system. They became part of the earth, part of the oceans, part of the living things that emerged from the primordial seas. And eventually, some of those atoms became part of you. The carbon in your cells, the oxygen in your blood, the iron in your hemoglobin, all of it was forged in stars long ago and far away. When you look at images of the universe breakers, you are looking at your ancestors in a very real sense. Those ancient galaxies helped create the conditions that made your existence possible. You are connected to them across billions of years and billions of light years. Understanding the early universe is not just an academic exercise. It is a way of understanding ourselves. It is a way of knowing where we came from and what made us possible. The universe gave birth to galaxies, and galaxies gave birth to stars, and stars gave birth to planets. And on at least one planet, life arose and evolved until it could look back at the universe and wonder about its own origins. That is the story we are trying to tell. That is what the universe breakers are helping us understand. So keep looking up, keep wondering, keep asking questions. The universe has more secrets to reveal, and you are part of the grand story of cosmic discovery. What do you think? Are we looking at a flaw in our math, or something truly alien to our universe? Let us know in the comments below. Thank you for joining us on this incredible journey to the edge of space and the beginning of time. If you found this exploration of the universe breakers fascinating, please like this video and subscribe to Cosmic Drift. And hit that notification bell so you never miss our next adventure through the cosmos. Until next time, keep looking up. The universe is vast and full of wonders, and we are just beginning to explore them. Before we truly conclude, let me take you on one final exploration into the depths of this cosmic mystery. There are still fascinating aspects of this story that deserve attention. Let us talk about the incredible precision required to make these observations. When JWST points at a distant galaxy, it is collecting photons that have traveled for billions of years. Each photon is a tiny packet of energy, and collecting enough of them to form an image or spectrum requires extraordinary patience and sensitivity. Consider the challenge. The universe breakers are so far away that their light has been diluted by the expansion of space. What started as intense starlight has been stretched and weakened until only a faint whisper remains. Detecting that whisper requires blocking out all other sources of noise. The engineers who built JWST had to account for every possible source of interference: heat from the telescope itself, scattered light from bright objects in the field of view, electronic noise in the detectors, cosmic rays striking the sensors. Each of these sources of noise was minimized through careful design. The sunshield keeps the telescope cold. Baffles block stray light. The detectors were calibrated with painstaking precision. Software algorithms filter out cosmic ray hits. Even so, detecting the faintest objects requires long exposure times. JWST might stare at a single patch of sky for hours, slowly building up signal until the distant galaxies emerge from the noise. It is a bit like trying to hear a whisper at a rock concert. You need to listen very carefully and filter out everything else. The fact that we can do this at all is a testament to human ingenuity. A few centuries ago, we did not even know other galaxies existed. Now we can image galaxies that formed when the universe was in its infancy. The progress is breathtaking. Let me describe what it is actually like to work with JWST data. When observations are completed, the raw data is transmitted from the telescope to Earth. This data goes through a series of processing steps that correct for instrumental effects and calibrate the measurements. The processed data is then made available to the scientific team that requested the observations. For the most exciting discoveries, teams often work around the clock. Time zones do not matter when you are chasing the secrets of the universe. Researchers in Australia might be analyzing data while their colleagues in Europe sleep, then hand off to Americans who continue the work. The analysis itself is done with sophisticated software tools. Astronomers use programming languages like Python to manipulate the data, fit models, and extract physical parameters. They compare their results to theoretical predictions and simulations. They check and double-check their work to make sure the conclusions are robust. When something surprising emerges from the data, there is a mix of excitement and caution. Is this real? Have we made a mistake? Could there be an alternative explanation? This is where the scientific community comes in. Results are shared with colleagues, presented at conferences, and submitted to peer-reviewed journals. Other scientists examine the analysis, looking for errors or alternative interpretations. Only after this scrutiny is complete are findings accepted as reliable. The universe breakers went through this process. Initial results were presented at conferences. The Nature paper was reviewed by anonymous experts before publication. Follow-up observations were conducted to verify the findings. The conclusion that these galaxies are real and challenging has withstood this scrutiny. Let me explore the concept of look-back time more deeply. When astronomers talk about distances in the universe, they often use a term called look-back time. This is the amount of time that has passed since the light we are seeing was emitted. For the universe breakers, the look-back time is about 13.2 billion years. That means the light left those galaxies 13.2 billion years ago. The universe was about 600 million years old at that time. But here is something that can be confusing. The actual distance to those galaxies is not 13.2 billion light years. It is much greater. The reason is the expansion of the universe. While the light was traveling toward us, space itself was expanding. The galaxies we are seeing have been carried away from us by this expansion. Their current distance is more like 30 billion light-years or so. This seems paradoxical. How can something be 30 billion light-years away in a universe that is only 13.8 billion years old? The answer is that the speed limit of light applies to objects moving through space, not to space itself expanding. Space can expand faster than light, carrying objects with it. So when we see the universe breakers, we are seeing them as they were 13.2 billion years ago, when they were much closer. But if we could somehow teleport to where they are now, we would find they have moved far beyond the observable horizon. This concept of cosmic distance is important for understanding what JWST is showing us. The ancient galaxies we see are not just far away in space. They are far away in time. They existed in a younger, smaller, denser universe that was very different from the cosmos we inhabit today. Let me discuss what we know about the environments where these early galaxies formed. In the early universe, matter was distributed more evenly than it is today. The cosmic web was just beginning to form. Dark matter was still clumping into the halos that would eventually host galaxies. The regions where the universe breakers formed were probably overdense. They had slightly more matter than average, which gave gravity a head start in pulling material together. These overdense regions would have been the first places where structure formed. Today, the descendants of those early overdense regions are the cores of massive galaxy clusters. The most massive clusters we see in the present universe probably trace their origins back to regions like those where the universe breakers formed. This gives us a way to connect the distant past to the present. By studying the ancestors of massive clusters, we can understand how those clusters assembled over cosmic time. The universe breakers are snapshots of this assembly process in its earliest stages. Some scientists have used this connection to predict what the universe breakers should look like based on what we know about present-day clusters. Others have worked backwards, using the universe breakers to constrain models of how clusters evolved. This interplay between observations at different cosmic epochs is one of the most powerful tools in cosmology. It allows us to test our understanding of cosmic evolution across billions of years. Let me tell you about some of the specific observational programs that are studying the early universe. JDS, the JWST Advanced Deep Extragalactic Survey, is one of the largest programs devoted to studying distant galaxies. It combines imaging and spectroscopy to characterize thousands of objects at high redshift. Many of the little red dots were discovered in JDS data. UNCOVER is another major program. It focuses on galaxy clusters that act as gravitational lenses, magnifying the light from even more distant objects behind them. By studying these lens regions, UNCOVER can detect galaxies that would otherwise be too faint to see. SEERS, the Cosmic Evolution Early Release Science Program, provided some of the first data from JWST and was where the original universe breakers were identified. It continues to analyze its rich dataset. RUBIES, the Red Unknowns Bright Infrared Extragalactic Survey, specifically targeted the mysterious little red dots. The cliff was discovered as part of RUBIES observations. Each of these programs has its own goals and methods, but they all contribute to our understanding of the early universe. The data they generate is used by scientists worldwide to test hypotheses and develop new theories. Let me reflect on the timescales involved in astronomical research. JWST was proposed in the 1990s, more than 30 years ago. Many of the scientists who conceived of the mission did not live to see it launch. The students who worked on early designs are now senior professors. This long timescale is common in astronomy. Major missions take decades to plan, build, and operate. The scientists who start a project may retire before it yields its most important results. This requires a special kind of patience and commitment. You have to be willing to work on something that might not pay off until long after you are gone. You have to trust that future generations will continue the work and build on what you started. The universe breakers are a payoff that nobody could have predicted when JWST was first proposed. The scientists in the 1990s knew the telescope would see far and see clearly, but they could not have known what it would find. They had to have faith that the universe would reward their efforts with discoveries worth making. That faith has been vindicated spectacularly. JWST is producing science that exceeds even the most optimistic expectations. The universe breakers are just one example of the surprises it is revealing. Let me bring this exploration to a close by considering what the future might hold. In the coming years, more and more data from JWST will be analyzed. The sample of known high redshift galaxies will grow from dozens to hundreds to thousands. Statistical patterns will emerge that are not visible in small samples. New theoretical frameworks will be developed to explain the observations. Some current hypotheses will be ruled out. Others will be confirmed and refined. Eventually, a coherent picture of the early universe will emerge. That picture might look quite different from what we expect today. The history of science teaches us that nature is often stranger than we imagine. The early universe might have operated according to principles we have not yet discovered. Or the picture might turn out to be an extension of what we already know. The lambda CDM model might survive with modifications, absorbing the new observations into an updated framework. Either way, we will know more about the cosmos than we do now. We will have pushed back the frontiers of knowledge and extended the boundaries of the known universe. And that is what this is all about: the pursuit of understanding, the drive to know, the conviction that the universe is comprehensible and that we can comprehend it. The universe breakers are not just interesting astronomical objects. They are milestones on the journey of human discovery. They mark a place where our understanding was tested and stretched. They remind us that the cosmos has depths we have not yet plumbed. So as you go about your daily life, remember that far above you, the James Webb Space Telescope is quietly collecting photons from the edge of time. It is watching the first galaxies take shape. It is witnessing the birth of cosmic structure. And the light it collects carries information that will help us understand our origins and our place in the universe. We are not separate from the cosmos. We are part of it. We are the universe becoming aware of itself. The universe breakers tell us that the cosmos was busy from the very beginning. It did not wait billions of years to start creating complexity. It began immediately, building galaxies and stars and the seeds of everything that would follow. In that ancient activity, there is something inspiring. The universe seems to have an inherent tendency toward creation, toward building, toward becoming more than it was. We are expressions of that tendency. Our curiosity and our science are continuations of the cosmic creative impulse. When we look at the universe breakers, we are looking at a moment early in that cosmic story, a moment when the universe was just beginning its long journey toward the complexity and beauty we see today. And when we ask how those galaxies form so quickly, we are asking a question that connects us to the deepest mysteries of existence. What is the nature of the cosmos? Why does it behave the way it does? What does it mean for us? These are questions worth asking. They are questions that make us fully human. And they are questions that the James Webb Space Telescope is helping us answer. So keep asking questions. Keep wondering. Keep exploring. The universe is vast and ancient and full of secrets, and we are just getting started uncovering them. Thank you for watching. If this exploration of the universe breakers and the mysteries of the early universe moved you, please like this video and subscribe to Cosmic Drift. Share it with someone who loves the stars. And remember, every time you look up at the night sky, you are looking at your cosmic home. You are made of star stuff, and the universe is your birthright. Until next time, keep looking up. The James Webb Space Telescope continues its mission as you read these words. Right now, at this very moment, its golden mirrors are collecting ancient light from the farthest reaches of the cosmos. Somewhere in that light are more secrets waiting to be discovered. More surprises that will challenge what we think we know. More mysteries that will drive us to ask new questions and seek new answers. The universe breakers were just the beginning. They opened a door into a cosmic era we had never truly seen before. What lies beyond that door is still being explored, and the journey has only just started. We are living in an extraordinary time for cosmic discovery. The instruments exist, the data is flowing, the questions are being asked, and slowly, piece by piece, the answers are emerging. What will we find next? Nobody knows. And that is exactly what makes this adventure so thrilling.